We're very happy to have Kevin Costello tell us about Twistor theory and vertex algebras.
Okay, it's like I'm not sure I'm going to get to the vertex algebras part, so I thought I'd spend most of the time reviewing some work by Penrose and Ward from the 60s and 70s, which is like, it's really very beautiful classical algebraic geometry, but for some reason nobody knows it. The people who do this are like in the physics, in the math physics group at Oxford or something like this. So different geometers know it, but I think the algebraic geometry community doesn't. So I thought I would try to explain this stuff in algebra geometric language. So as a starting point, we know the following fact. So every harmonic function on R2 is the real part of a holomorphic function. Right? So the start of Twistor theory is generalizing this to dimension 4. Maybe a better way to say it is to say that a complex valued harmonic function is holomorphic plus anti-holomorphic and then we have to mod out by the fact that the constants appear in both. Okay, so to generalize this statement to dimension 4, well, we first run into a problem. On R2, there is one complex structure and its complex conjugate, but in R4, there are many complex structures. So let's parameterize them. So the complex structures which are compatible with orientation of course, this quotient, the SO4 mod U2. So any complex structure can be moved to some kind of standard one by some matrix in SO4, and the symmetries of the standard complex structure is U2. So it's this homogeneous space. And if we recall, spin 4 is SU2 times SU2. This is the double cover of SO4. And similarly, the double cover of U2 is SU2 times U1, where this U1 is embedded here as the Cartan, as the maximal torus. We see that the set of complex structures in O4 compatible with orientation is SU2 mod U1, which is CP1. Okay. So this statement up here, that every harmonic function can be built from a holomorphic and anti-holomorphic function, there's going to be a version of this on OR4, but instead of being a sum, it will be an integral. So the Penrose transform, the kind of very basic version, looks like the following. Every C-valued harmonic function is an integral of holomorphic functions where we integrate over the complex structures. So this is the statement we're going to aim for. But to make sense of this, we have to introduce complex manifold called Twistor space. So any questions so far?
Yes, I'm trying to relate the two statements for R2 and R4.
Uh-huh.
So the, SO2 is of course the same as U1. So it's 1 as opposed to 2, which the anti-homomorphic suggests that there should be 2, which maybe means you shouldn't be preserving orientation. Yes.
It's true that in the OR2 case, you don't look at orientation, whereas in the OR4 case, you do.
Why the extra?
I don't know.
Okay.
Okay, so on OR4, there's a CP1 of complex structures. If I take a point Z in the CP1, gives a complex structure on OR4. So as Z varies, this manifold, I just take the product, but I give this copy of OR4 a complex structure which depends on where I am. This becomes a rank 2 holomorphic vector bundle. On CP1. So as a complex manifold, it is O1 plus O1 and it's called ET, projective Twistor space. So it's like as a real manifold, it's OR4 times CP1, but as a complex manifold, it looks like this. So we can see why it looks like that in a second. So let's give OR4 coordinates. So I'm going to choose some reference complex structure. And then Twistor space has coordinates V1, V2, Z. where Z is on the CP1, V1, V2 on the O1 fibers. So these are just coordinates in a patch. And these are related by or 4 by saying V1 2 is U2 minus C over 1. Okay. So what's going on here? We're just seeing that if I fix Z, you define a complex structure, and U1 plus Z U bar 2 is the holomorphic coordinate in that complex structure. So when Z was 0, we get our original holomorphic coordinates, U1 and U2. When Z is infinity, we get their complex conjugates. And for the other values, we get this kind of interpolating family of complex structures with these coordinates. Okay, what else do we need to know? So if I take a point, say, x in over 4, there is a corresponding CP1 in Twistor space, because Twistor space is, after all, or 4 times CP1. And we call this just like CP1 sub x. So now I think we're ready to state, well, unless there's any questions, we can try to state the first version of the Penrose transform, which is the generalization of that statement over there. So theorem. So there is an isomorphism between one complex valued harmonic functions and secondly, the Czech or R-Dolbo cohomology group or Twistor space O minus 2, values in O minus 2. So here's how the map goes. O minus 2. Then alpha restricted to the CP1 at x is a class in H1, CP1, O minus 2. And O minus 2 is the canonical bundle of CP1. Now, on each CP1, therefore, alpha is a 1-1 form. It's something you can integrate. Like it's a first cohomology class with coefficients in the canonical bundle. So the harmonic function f of x is integral over the CP1 of alpha. So this formula takes a class here, turns it into a function. the statement, the content is, firstly, this function is harmonic, and secondly, that this map is a bijection. Okay. And I hope you can see it's a little bit like what I promised it would be. It's kind of an average because this CP1 parameterizes the different complex structures, so it's kind of an average over complex structures. Any questions? No, we have to prove that. So yeah, that's the first thing to do. So I'm assuming in this audience, everybody is happy with the cohomology of coherent sheaves and stuff.
What is the context of -2? So this PT is not like, are you taking, what kind of sections are you taking?
Well,
Are you taking,
you could either, if we took, I want to take complex analytic cohomology,
yeah,
and this would give me all harmonic functions.
okay,
If I took complex algebraic cohomology,
Yeah.
we would get harmonic functions of polynomial growth. So it would be harmonic polynomials. So here's the idea of the proof. I'll give you the proof that F is harmonic. So we'll write Twistor space as a union of U union V, where U is the locus where Z is not equal to infinity, and V is the locus where Z is not equal to 0. So U and V are both C3. And U intersection V is C2 times C star. So I'm just gluing Twistor space from 2 patches based on the obvious way of gluing CP1 from 2 patches. Now, check H1 is equal to the collection of functions like this, gamma V1, V2, Z, dz, where Vi are in C and Z is in C star, modulo those gammas that extend over 0 or infinity. So this is just writing down what if the meaning of check H1. It's important that the dz appears here because when we say extends over infinity, we have to take into account that dz is a second order pole at infinity. And these coordinates v, there's some transformation properties at infinity as well, which we're not going to worry about too much. So as you hopefully learned when you studied algebraic geometry, if I have a check cocycle and I want to explicitly integrate it over CP1, how do we do that? Well, that's just a contour integral. Because my check cocycle is defined on the C star inside of CP1, and its integral is just the contour integral around a circle in that C star. So F, this F of X, I'll write it as F of U bar, is then contour integral, the locus z equals 1 of so I've taken the contour integral and I've used the relationship between coordinates in R4 and coordinates in Twistor space to substitute in u1 plus z u bar 2 and so on for v1 and v2. So this is a very concrete expression. We've said our function is an average of things, each of which is holomorphic in some complex structure. This expression this is harmonic. So there's two ways you can see this. Firstly, any function on R4 which is holomorphic in some complex structure is harmonic. Right. Why is that? Well, we can use the SO4 symmetry to say our complex structure might as well be the standard one, and then it's obvious. Or two, we just explicitly compute exercise. I just explicitly check. Okay. It's kind of completely obvious. You just differentiate respect to u1, and u1 bar is like differentiating with respect to the first coordinate and the second coordinate, whereas differentiating with respect to u2 bar and u2 is also differentiating with respect to the first and second coordinates, but they come with a different sign. So it just cancels. Okay, this implies f is harmonic as it is an integral of harmonic things. Okay, so we've sort of seen the very basic start of the Penrose transform. We've seen that everything in here does indeed give you a harmonic function, and it's explicitly an integral of things which are holomorphic in one of the complex structures, exactly like we saw for R2. So there's, of course, a bunch more things to check. Yeah. Yeah, it's because you have to go it's how Self-duality works when we write things in terms of check homology. So when I write this as an integral, we're probably thinking in our heads that I've written my cocycle using the Dolbeau language, and it's literally an integral of a 1-1 form. But we know Dolbeau cohomology and check homology are the same, so that integral map must make sense on check homology too. And there's a little kind of translation you need to do to figure out what it becomes. And it, because check 1 cocycles are things defined on the overlap, you kind of immediately guess it has to be a contour integral, and it is. it might be worth saying this contour integral obviously vanishes on things that extend over 0 and infinity, because if they extend over 0 and infinity, I can shrink the contour. Okay, any other questions? Yeah.
Are you gonna say something about the other direction?
Like, why is it an isomorphism?
Or like how to, if I given a harmonic function, how to get a cohomology?
I'm sure there's a better proof, but the only way I would know how to prove this would be to write down this map and then compute the character of both sides as a representation of SO4.
Oh.
And that's not a.
So there's no like nice map.
There might be, I just don't know it. In fact, there probably is. There probably is. I'm just. I mean,
Sorry, what do you mean the character? I mean, these are both infinite dimensions.
well, the character under the action of SO4 times scaling.
Ah,
So each eigenspace under scaling is a finite dimensional representation of SO4. I mean, you can write a map back the other way if you start with a plane wave, use the Fourier transform. So I can that's a kind of helpful thing. So I'll write that down too. So firstly, well, how do we know this is surjective? So a basis for harmonic functions is given by things like E p dot x, where E in C4 satisfies P dot P equals 0. Right, so just using the Fourier transform to write down a basis for all functions and saying, well, those which are harmonic, that means the momentum vector must be null. So here's the following fact. If so, P is null if and only if the linear function x goes to p dot x is holomorphic in some complex structure. Okay. Well, why is this? Well, this is another piece of classical algebraic geometry, really. We're looking at null vectors in C4. That's a quadric in C4. So once I projectivize it, so if I divide by C star, this is a quadric in CP3, and that's CP1 times CP1. So for these two CP1s, one of them is the complex structure. And the other is equal to the linear holomorphic functions in that complex structure. So I'm not sure I explained this very well, but this is roughly why this is true. Okay, so once we know this, it's kind of obvious. Like if you give me something like E P dot X, how do we get it from here? It's actually slightly easier to write this, let's say, Dalbo language, but it doesn't really matter. So E P dot X comes from a class in H1 ET O minus 2, which is like, so it's a delta function at some point in the CP1, because things are going to be holomorphic in that complex structure, times an exponential of V1 and V2. So this is a very, sorry, I didn't explain this very well. It's a very brief sketch of why this map is surjective and how you can take a plane wave and explicitly lift it to Twistor space. So if you really wanted, the algorithm would be take your harmonic function, Fourier transform it, and then write it in Twistor space in terms of some kind of integral of these guys.
Obvious obstruction is that this isn't obviously the delta function.
I mean the delta function in the Dalbo sense, which is a 0-1 form.
Yeah.
So delta, it's really like d bar of dz over z minus z.
Oh, okay.
That's actually, okay. So this is the basics. So we explained first chief cohomology of Twistor space, values in O minus 2 is harmonic functions at O4. So the really interesting part of this story, though, is that you can also see how to solve nonlinear PDEs as well as linear ones by using algebraic geometry on Twistor space. So maybe I should move on. This is a really beautiful piece of kind of geometry from the 70s. Unless there's any questions about this basic case of harmonic functions, I should try to move on to that.
Question, but look at this theorem, but part 2 has a kind of obvious rational structure, right? So it says it can be defined as vector space of rational numbers.
Yes.
So it means that space of harmonic functions has a rational structure.
But it's kind of a silly one. You just expand in Taylor series and ask if the coefficients be rational.
The exponential series where it is 0.
They're 0, yeah. Like you just ask it all, if you have a harmonic function, all of whose derivatives at the origin are rational or something like that. It's the, like harmonic polynomials are dense. Harmonic polynomials have an obvious rational structure.
Yes.
And then we extend that to the vector space.
Okay.
So
Sorry, and then but if it's about harmonic functions, do you have some growth conditions?
it depends what kind of cohomology you mean. If you mean like complex analytic check cohomology, then it's all harmonic functions. But if it was complex algebraic, then they would be of polynomial growth.
If it has polynomial growth, it's true that all derivatives also have polynomial growth.
Yes, anything with polynomial growth is a polynomial because It's an elliptic PDE, so it's an analytic function. An analytic function is polynomial growth at polynomial. Okay. So the word correspondence is a really cool generalization of this. Says the following. There's an isomorphism. It's really in a very nice way of stacks or something like that. It preserves all symmetry between holomorphic vector bundles B on Twistor space such that for all x in O4, the restricted to this CP1 is trivial. It's important that it is trivial. It's not trivialized. I'm just saying there exists a trivialization. And two, bundles on O4 with connection which satisfy Self-duality equations.
Bundle is not trivialized, but there exists trivialization.
Mm-hmm.
Fact, right?
It's not compact, no.
So
It's like it's CP3 with a line removed, with a CP1 removed. So if I was to do the Twistor space of S4, it would be all of CP3. And then this would be compact, but then this equation would be an elliptic equation on a compact manifold. So it would all.
true state of this, for instance, you need the like all homomorphic bundles and
Yes. I mean,
so there's again no growth conditions in it.
no, these spaces are, both spaces are like infinite dimensional. Well, I'll tell you what I mean by the self-duality equations in a minute. You probably have seen them. So to prove this, it's useful to replace R4 by C4. So we actually, before we get to the proof, we're going to have to do a little bit of background on generalizing the Twistor correspondence. So once I complexify R4 to C4, I have to explain how this is related to Twistor space. Well, turns out that C4 is equal to the set of lines in Twistor space, which are linearly embedded. So how do we see this? Well, Twistor space is equal to CP3 minus CP1, and lines in CP3 is the Grassmannian DR24, and C4 is a big cell of lines that don't intersect infinity. Okay. But we can be even more concrete. More concretely, Twistor space is O1 squared, CP1. The space of sections is C4, because each O1 has two sections, and there's two copies of O1. So every point in C4 gives us a line in Twistor space, which is just one of these sections. So as part of the word correspondence, we need to understand a little bit about how Twistor space encodes geometry. Sorry.
Space, total space of O1 squared of C1.
Yes.
Then H0 of O1 squared is C4.
Yes.
So how does the point of C4 define a line?
The image of the section.
Sorry?
I just take this section. Yes. Okay. So if I take a point X in C4, we get a kind of CP1 X inside of Twistor space. So C4, it's not just a vector space, has an inner product. So we can ask, how do we see this inner product by thinking about Twistor space? Well, a vector X in C4 is null if and only if CP1 X intersects the zero section. So the data of my inner product, or at least the data of which vectors are null, is encoded in the geometry of these lines and whether they intersect.
You say that C4 is a product. What does that mean?
Well, there's an action of yeah, I should have talked about the symmetries of everything.
I understand you can try to move in opposite direction. You can start with total space of O1 squared.
Mm-hmm.
And then we can take global section of O1 squared. That gives you some kind of C.
Yes.
You're saying that that space comes included within the product.
Oh, defined up to scale.
Sorry,
Well, the way I've written it, it depends how much.
what sense is it not?
It depends how much structure I've put on Twistor space. So if you take Twistor space just as a complex manifold, then that inner product is defined up to scale.
Scalar.
Yeah,
How?
by this formula. Because to define it up to scale is to give me a quadric.
Just the big global section of O1 squared. Right. I mean, you want to say that each one will be like Lagrange out there, or
No, I mean, it's just,
have some, have
I mean, if I take,
two-dimensional plus two, they focus. Then you want to put something above.
yeah. So I take two-dimensional, it's like the two-dimensional representation of SL2, I'll call it S plus, and then I'm taking two copies of it. So this is a symplectic form, and my other copy of C2, I'm giving it a symplectic form as well. When I tensor it together, I get a symmetric form. So
So say this whole one squared means it's whole one times symplectic two-dimensional vector space.
exactly, yes, absolutely. And more generally, if I had something fibered over CP1 in holomorphic symplectic manifolds, there would be a nonlinear version of this. And you would find a four-manifold with a metric with some nice properties. But if you want to be really kind of really down to earth, let's see. You know, if I take a vector x in C4, gives me two sections of O of 1, namely, say, x1 plus z x2, x3 plus z x4. And these, the condition that these have a common zero I'm just checking that this condition is indeed a quadratic cone, is that the determinant of this matrix is 0. Right? So that's indeed giving you some kind of quadratic condition on the axis.
And these coordinates are quadratic form instead of
Yes. Okay, where were we? So I haven't explained what this is yet. So I want to recast this in terms of complex geometry on C4. And this is an okay thing to do because the Self-duality equations are elliptic equations. Any solution of an elliptic equation is analytic and can be extended from R4 to C4. And something similar will happen here.
rank 1. You literally get the state.
Yes, because like you can write pretty much it'll be H1 of O, and but then instead of H1 of O minus 2, but there's an exact sequence saying relating H1 of O, H1 of O minus 2. Yeah. Would you like to write that out? Okay. So example. In the case of rank 1, we're saying H1 PT O is solutions of self-dual Young-Mills in the abelian case. So these guys are really closely related to harmonic functions. There's a map like that, because O minus 2 is a subsheaf of O. These are harmonic functions. So we would expect a map like that. It's not. Neither of them are injective. Because if you look at the exact sequence, this will be H0 of PT, structure sheaf at C equals, say, 0 plus the structure sheaf at C equals infinity. And this will correspond to holomorphic plus anti-holomorphic functions. So this sequence is exact, and this one is exact too. Oh, C is a coordinate in P1. So how do we get this? So if phi is a function, then I said A equals d bar phi. The claim is that this satisfies the self-duality Mills equations if and only if phi is harmonic. This is because if I look at the curvature of A, the self-duality Mills equations are that F02 vanishes. That's obvious because that's d bar of this. F20 vanishes. And then the Kähler form wedge F11 vanishes. Now the Kähler form wedge F11, this is like Kähler form wedge del bar phi, and that's the Laplacian of phi. Okay, so the self-duality Mills equations are just the statement that this is harmonic. And we can also see, well, if I add an anti-holomorphic function to phi, this doesn't change. But of course, my connection is only defined up to gauge transformations. So if I add a holomorphic function to phi, that will change it by a gauge transformation. So that's why this sequence is exact.
Well, gauge transformation is the sort of so when you're saying the solutions of this equation, you can see them up to what?
It's a connection up to C infinity gauge transformations, yeah.
But I think that if you add to this thing a holomorphic function, then it doesn't change.
Yeah, because if what am I saying? I'm messing something up. The point is, if I add something holomorphic, this literally doesn't change. Because d bar of the holomorphic thing will be 0. So A minus d phi is del phi. So these are gauge equivalent. So I'll leave this up. Okay, so how do we so in order to state the theorem cleanly, we need to talk about complex versions of self-duality Mills equations. So let me try to do that quickly. So complex bundles on C4 with a kind of complex analytic connection. Well, the self-duality Mills equation makes sense here. Self-duality Mills equations. And there's a really nice geometric way of saying this. For each P in C4, a collection of null planes well, this turns out to be, it has two components. And the self-dualing those equations is equivalent to my connection is flat for planes in one of the components. Okay. So any condition about curvature, curvature is the failure to be flat. The components of the curvature tensor are the failure to be flat on some plane. So the geometric way of saying self-duality is I take one of the components of the space of null planes and ask on every such null plane, I want it to be flat.
There's a statement here.
Yeah, I mean,
Well,
it's a really trivial statement. So you look in your textbook for the definition of self-duality.
yes.
That's
It's
three.
actually done on 4, not C.
Well, it works in C4 too, right? Because all we're saying is that the curvature has 6 components and 3 of them are 0. That's that. So self-duality, the exterior square of C4 equals the adjoint of SO4C. So that's SL2 plus SL2. And self-duality means the components of F in one of the SL2s are equal to 0. So that's an equation that makes sense over any field. Yeah, anytime we have this in the algebra, any field of characteristic 0.
And when you field of bilinear form over the field,
Yeah, although I suppose I actually
that's for the same type.
certainly in characteristic 0, we're just relying on this the algebra isomorphism. And then, okay, so this is some equation. And the observation is that it's the same as this one, that on certain null planes, the curvature vanishes. And it's a really trivial observation.
It's saying connections flat for planes in one of the components.
Mm-hmm.
Confusing. It's not like canonical. How do you say which one is one, which one is not?
Well, one of the components is a homogeneous space with this SL2, and the other one is a homogeneous space with this SL2. So the choice of component is the same as the choice of which SL2 you're making. And that distinguishes.
It's three aligned. Yeah, well. Because you have to sort of say it uniformly for all tangent spaces.
Yeah, but this, if I didn't trivialize the tangent bundle, I would say the set of null planes is a homogeneous space for SO4, and it's this homogeneous space. It's the associated bundle to some SO4 homogeneous space.
If you mention something
So globally, it has two
that's
components?
not simply connected, maybe these two components could have mixed up, right?
Yes, I suppose that's possible. Yes.
So the assertion is global here.
On C4, globally, there are two components, but I was to do this on some other manifold with some more interesting topology. Sasha's point, these two components might get mixed up,
Right.
but let's not worry about that. But that, I mean, that would only happen if somehow these two things, the two pieces of SO4 got mixed up. Okay, so if we're willing to accept this, let's.
So it's a question of which kind of polynomial. Whether it belongs with respect to that.
Yeah. Oh, if it has SO4 holonomy, it's totally fine because the adjoint action of SO4, of course,
Yeah.
it doesn't switch those. Yes, absolutely. Okay. So once we know this, willing to believe this statement, now let's construct the functor. So if V is a holomorphic bundle on Twistor space, and V restricted to each CP1 is trivial, we define a new bundle WV on C4 by WV at X, its fiber at X is H0 on that corresponding CP1 of V. Okay. Now, of course, this is the first thing any algebraic geometry person would do. It's just a push-pull construction. Now, I need to show that this has a connection which satisfies the self-duality equation. So a connection, so we need to give an isomorphism WV at X, the fiber at X to the fiber at some point, which is a first order deformation of X. Yeah.
Is there a map from Twistor space to C4 that's holomorphic?
No, it's a correspondence. Because the Twistor space, is an open subset of the Grassmannian, GR24. So
Oh, okay. So you're using this.
yeah, there's like CP3, flag variety. There's a correspondence like this.
Oh, right.
And we're restricting this correspondence to an open subset here and here. Okay. So, but in any case, every point here gives rise to a CP1 in Twistor space. And my bundle we get by taking the cohomology along that. So we're just doing the push-pull along this correspondence. So I need to say the fiber at some point X and some nearby point are the same. Well, the tangent space at a point X in C4 is spanned by null vectors. it in fact is equal to the tangent space of the null cone. Because the singularity, the origin in the null cone, means the tangent space gets bigger there and is equal to the tangent space of all of C4. So it suffices to give an isomorphism between the fibers where Y is null now comes the clever part. Y is null if and only if the CP1 these CP1s are non-empty. So here's the picture. This is the CP1 at X, CP1 at Y. I'll write this out again in a second. Because my bundle is trivial, sections on this CP1 is the same as the fiber at the intersection point. And that's the same as the sections on this other CP1. So as long as they intersect, we get a canonical isomorphism from here to here. So if I is equal to the intersection point, sections on one CP1 is equal to the fiber at I canonically, and that's equal to the sections on the other CP1.
Are we proving this word correspondence now?
Yeah, we're proving the word correspondence. I'm constructing the connection. Saying the fiber is the H0, and if I have two nearby points, I'm going to give an isomorphism between the fibers, and it's given by this formula. Okay, take my section, restrict it, and then extend it over this one.
The CP1s really are linear, like degree 1.
Yeah, absolutely.
So they can't intersect at more than one point.
Yes, absolutely. Okay. So now let's prove. We need to prove that this satisfies self-dualing Mills. Implies that the connection is flat on certain null planes. So, yeah.
Still stuck in this track.
Mm-hmm.
Is this obvious? Maybe it's because it's a quadrant. Is it obvious that what you get is kind of linear in line? This isomorphism.
Well, because
So these form a basis. Is that the null tangent vectors? And like
yeah.
And this is the degree 2 thing. Is that?
I suppose you're worried about. Let's
That
see.
there could be multiple y's that are linearly dependent, like that are.
No. The point is the tangent space of the null cone
Oh, okay.
is the same as the tangent space of the.
No, but sorry, what do you mean by the tangent space of the null cone? It's a singular thing. So you mean that?
I mean that as you would read it in Hartshorne.
Yeah, but you can only move in some directions.
I mean, you can have a curve. Like if I take what's it like an arbitrary curve in the ambient space.
Yeah.
is tangent to the cone to first order, but not to second order.
Yeah.
And so you might be worried about, if I take an arbitrary curve, this construction doesn't tell me how to move to second order, only to first order. But that's all we need.
Okay.
Are you convinced?
I think so.
1 second. Okay, so the final thing is, why is it flat on certain null planes? So if I take, here's my CP1 of x, and here's some point I, the space of CP1s in Twistor space, which intersect I, well, how do I get that? I'm going to look at H0 of the normal bundle, and I want my section to vanish at I. One minus I, oh, 1 minus I. And because they vanish at I, this is a copy of C2 inside of C4. So this CP1s, which intersect here, the body, is a null plane. There?
No, before this.
Ah, yes. So it's null as any two to intersect. Right? Remember the condition of being a null vector is that it intersects the zero section. So any two of these lines intersect each other, so they're all null separated. So the self-duality equation then amounts to saying, on this copy of C2, it's flat. So now it should be kind of obvious that the connection is flat. Because how did I define my connection? I said, now I take a section on some curve. To relate it to a section on some other curve, I just said, oh, they intersect. And I compare the fibers at this point. So it doesn't matter which path I chose to relate them. It's always just the fiber at this point. So this is just completely obvious. I don't know. I thought this was super cool. Yeah. It's because I'm looking at H0 of O1 with, sorry, CP1 of O1 tensor C2. That's H0 CP1 O1 tensor C2. And these null planes are somehow associated the lines in here, whereas the other ones are associated with lines in here. In fact, I should have said this in the beginning. How do I get null planes? C4 is C2 times C2. It's a tensor product of two symplectic vector spaces. And a null plane can be Lagrangian tensor symplectic or symplectic tensor Lagrangian. Those are the two components. Okay, yeah.
So this like parallel transport isomorphism seems like completely trivial, right? If it's like just the fiber of the intersection.
It's trivial on these planes, but there is interesting curvature. If we can write down a path like a loop in C4, like an algebraic loop, on which there's interesting curvature. So I'll do the following. Consider three CP1s that form a triangle. Like this. So what does this correspond to in space-time? So x1, x2, x3 are in C4. And this intersection point, x1, 2, is a null line from x1 to x2. And similarly, for x1, 3. So this picture corresponds kind of dually to something like this. Yep. So you were objecting that like this construction might just give me a flat bundle, which would be bad because then it couldn't be an isomorphism, because not all solutions of the self-duality Langlands equations are flat. So I want to demonstrate how you can see the curvature of the bundle by thinking about this kind of triangle. So in the physics literature, they would call this like a null polygonal Wilson line, because it's, a polygon whose sides are null. So parallel transport around a null polygon, say null triangle, is equal to the map where you take, say, H0, CP1, X1, are restricted to the fiber at X1, 2, X2, are restricted to the fiber X2, 3. What am I doing? E1, X3, restricted the fiber at X1, 3. So by using the isomorphisms between sections and the fibers, you can go around this triangle in a kind of algebraic parallel transport, and there's no particular reason that that's the identity. And in fact, it isn't. You can, if you build a holomorphic bundle, you can compute this. Okay, any other questions?
Like, this is the comment you made about how they're not all trivialized. Is it, or-
Yes, they're not exactly, yeah. Like I draw this triangle in CP3, and if I look at a little neighborhood of that triangle, my bundle is not trivial on that region, even though it is on each CP1. So the last thing I wanted to maybe spend a few minutes on was the ADHM construction. So I think this history is basically, so Ward came up with this result at some stage in the early 70s, and ADHM realized that if you could understand vector bundles on CP3 and classify them, then you can use this theorem to classify solutions of the self-duality Mills equations. So that's great because now you've translated this hard problem in PDEs into something purely in algebraic geometry. How do I classify vector bundles on CP3? So nobody had done this before, but yeah, I'm being a bit. The ADHM was about vector bundles in R4, which trivialize at infinity. So they extend to the 4 sphere. So that amounts to putting in this extra CP1. Then you're looking at holomorphic vector bundles in CP3, which trivialize.
What is the precise statement? The morphing bundles, the groupoid of holomorphic bundles on CP3 is equivalent to what?
The groupoid of solutions of the self-duality Mills equations on S4.
S4. Just on S4 as it is.
Yes. And then if you ask your bundle to be trivial at the CP1 at infinity on CP3, then they're correspondingly trivial at the point at infinity on S4. Okay. So in any case, so there was this construction by a guy called Horrocks who was able to write down explicitly certain vector bundles on CP3, and they used this as part of their classification. So how do I build a bundle of P? So here's the ADHM construction. So the bundle is the cohomology of a complex bundles that looks like so in degree 0, I'm going to put a bunch of copies of the structure sheaf. In degree -1, I'm going to put O -1. And degree 1, I'll put O of 1. Here is some matrix, I of Z. This is like V2 plus X. So if you remember, V1, V2, and Z are coordinates on Twistor space. I'm not trying to write down the most general bundle on Twistor space, because part of the constraint they had was that as you go off to infinity, your bundle should look like the trivial bundle, because as you go off to infinity, you should get the trivial instanton. So that's why I said that these matrices X, Y, and I and J, they only depend on Z and not on V1, V2. So Y are these are order 1 polynomials, and Z, and this is a complex. This equation is satisfied. So this is an order 2 polynomial. So this is really 3 equations, namely the coefficients of 1, Z, and Z squared.
Is there a reason to look at complexes of this form?
Yeah. So let's look at what happens when V is very large.
Yeah.
Then I can drop all of these X, Y, I, and J. They're kind of subleading. And then this top piece is the Costello complex, which resolves the structure sheaf of CP1. So when V is very large, it looks like the trivial bundle, plus the structure sheaf of CP1 located at the origin, well, that's gone. So when V is large, it's the trivial. So that's one reason why you would. I don't know. I was having this conversation with Sasha the other day. It kind of looks like it's built from the structure sheaf plus the structure sheaf of CP1 glued together in some way.
Okay.
So that's the best I can say.
But so at this point, is the answer basically that you have to be ADHM to
Or indeed Horrocks.
what's that?
R.G. Horrocks, whoever he was.
Yeah.
He just wrote down the rank 2 case in some random algebraic geometry paper. I see. But there was other algebraic geometers involved as well. But like at some point, you have this construction. There's some kind of non-trivial theorem that indeed every bundle arises this way.
Right.
Okay, so this construction, so the H0 of this is, in good cases, like with generic matrices, a rank n bundle on PT with second Chern number equals to k. So this means by Ward, it gives me a solution to the self-duality equation. But there's a bit of a subtlety which I've been eliding. Normally, when you want to solve the self-duality equations, you want your connection to be a unitary matrix. But we didn't have that. It was just an arbitrary matrix. Now, if we want to get UN, then we need some kind of reality conditions. So for example, if I expand I as I0 plus Z I1, similarly for J, X, and Y, the kind of thing you might want is like I0 is J1 dagger, X0 is Y1 dagger, this kind of thing. I forget the details, but there's some condition that some components are the Hermitian conjugates of some other components. So if you do this, it looks like we've started off with loads and loads of matrices, like so. So before imposing reality, we had two n by k matrices, two k by n, and four k by k. And these are all complex. And then three complex equations. So this final step is just to bring you into the form of ADHM you might have seen before. So after imposing reality, these things are no longer independent. So we get one n by k complex matrix. Similarly, one k by n, and two k by k, and three real equations. Okay, I mean, yeah, maybe this is a good place to stop. So what do we? So we sort of sketched how you go from a holomorphic bundle in Twistor space to something satisfying Self-duality and Mills, and then explained that ADHM realized that you can classify solutions of Self-duality and Mills in this way. Okay. Any further questions?
Instead of the Twistor space, make like the bubble space of a solid white bundles.
I think there's always going to be, let's do something simpler, right? Like, instead of taking O1 plus O1, let's take O2 plus O2 or something. So there's always going to be some kind of correspondence between vector bundles on my complex variety and like vector bundles on the moduli space of CP1s in that variety. But I don't think you'll ever get anything quite as clean as this, where the moduli space of CP1s in my variety is, or4, and that the equation becomes this nice equation. No, true, but I mean the algebraic geometry side is going to be there.
Same space.
Yes.
So, but can you see this correspondence? Can you see this correspondence to algebraic?
You'll make out correspondence.
No, the combination of this.
There's one between two holomorphic functions.
Well, the map is just I take a holomorphic bundle on Twistor space and I restrict it to one of the fibers. That's a holomorphic bundle on C2. But the fact that this, yes, yes, absolutely. So maybe in the case of a hyperkähler manifold, it's much easier to talk about things.
Just say it. You don't forget about the existence of real numbers.
I think, let's see.
That's what they always like.
Yeah, probably the thing to do is, okay, you want to compactify Twistor space, but not to CP3. You want to compactify it into a P2 bundle over P1. And because we're always talking about bundles trivialized at infinity anyway, that's not really going to make any difference. And then you'd say, well, a holomorphic bundle on this, I can just restrict it to a P2 fiber, and that's the map.
Then they want to say that the snow is kind of a projection.
Yes, and that seems really non-obvious.
That's purely that's a statement of fundamental truth.
I suppose so. But yes, it's certainly a statement in, it's definitely a statement in pure algebraic geometry. But it's only a bijection if we impose these reality conditions, though. Everything's holomorphic, but bundles on holomorphic bundles in Twistor space will give me Self-duality equations for the group GLNC, whereas the Uhlenbeck-Yau theorem is about solutions for the group UN. So you get something kind of twice as big.
But okay, so can you inform what gets bijection? What kind of homework?
Okay, so if I want to get a UN thing, you have to also allow yourself to talk about the real structure in Twistor space. So it'll be something in real algebraic geometry.
It's impossible to say. Really.
Yes, but it's not crazy though, because there's a perfectly nice real structure in Twistor space, and you're talking about algebraic bundles compatible with that structure.
You're saying that it should be a algebraic bundle defined with real structure.
Yes, exactly. That's what this
Real algebraic bundles space structure.
complex.
Bundles.
Yes, exactly. Yeah. Okay, so I should maybe just stop there.
It's going to be the vertex algebra.
There's 12 vertex algebras you think about. Take a bundle and Twistor space and then restrict it. Yeah, I might keep it starting and then all of that. That's like
That's somewhat.
some
Okay, yeah.
it's like loops into like maps of C star times C times C. So that's part of the interesting.
Oh, come back and explain. Yeah, thanks.